A lot of us have been so looking forward to this fireside with these two amazing people. And I will quickly introduce John and Dave, who everybody knows who they are. But just to remind you, John Hennessy, who's now the chairman of Alphabet, and Dave Patterson, who's now a distinguished engineer at Google. And that's what they call it, right?
Distinguished engineer.
Yeah, distinguished engineer at Google. And they both wrote the hardware architecture book that most people use to learn hardware architecture. In fact, 2 versions of it now are out. And of course, they developed the RISC architecture together, and then they just won the Turing Award together. Great YouTube video of their speech about that. And the Turing Award citation was for developing architecture approach to design evaluation of computer architecture while with enduring impact on the microprocessor world industry. And John came to Stanford as a professor in 1977, began the MIPS project in 1981, was director of the computer systems lab for 89 to 93, and I normally wouldn't mention that, but that was when he recruited my husband to Stanford, and that was when I met him. And then, of course, was an amazingly impactful president of Stanford for 16 years, from 2000 to 2016. And then Dave joined UC Berkeley as a professor in CS in 1976. And of course, he co-led the RISC project starting in 1980 and coined the term RISC. He has an amazing way with names. And that was when I met him because I was in his architecture class at Berkeley. And I'm sure he didn't remember me from that. But
I remember. What grade did she get, Dave?
Oh, A plus. I'm sure that's what it was.
And he retired after just about 40 years at UC Berkeley in 2016. And both have an amazing legacy of graduate students. And I just noticed on Wikipedia, I didn't know this, but Dave has been the highest contributor to a charity bicycle ride for MS. He was the highest from 2006 to 2012. It sounds like you stopped riding it. It's a 2-day event.
Yeah,
okay.
Yeah.
But another nice thing about both of these people, I mean, they've spent their life in service to the world, but they both have been married well over 40 years to the same person.
No, wait.
I don't think it counts if it's not the same person.
No, there's 2 different women. We're not married. We're not.
You share a lot, but not
this is how rumors get started.
Okay. So neither of you grew up near Silicon Valley, and it was back in the 70s. Since your PhDs were mid to late 70s, it must have been even earlier than that you got interested in EECS. And that was a while ago. What caused you to do that?
I'll give my story first. I was a math major at UCLA. This was before you could get a degree in computer science. And I knew computers existed, but it never crossed my mind. Nobody whispered computers in my ear like the graduate plastics. So a math class was canceled. I took a half-unit course at UCLA at the end of my junior year. It was Fortran with punch cards, but still, it was the ideas from my mind came alive in the computer, and I was hooked. And so I did a do-it-yourself computer science major my senior year from business and engineering classes, and then stumbled into graduate school because somebody got me a job as an undergraduate and stuck around after that.
So I actually had my first encounter with computing when I was in high school. We had time-sharing machines and paper tape. I mean, it was really bizarre. And then I undertook a science project to build a machine that plays tic-tac-toe. built from surplus relays, believe it or not, because at that time, that was what I could afford. It worked. You know, if you know about tic-tac-toe, you know you never lose if you're smart, right? So, and lots of people are not so smart, so the machine would win a lot. It was sufficient to convince my then girlfriend's family that maybe I was going to do okay, and that's the person who's now my wife. So that worked out well from that perspective as well.
That's amazing.
And then I headed to college. I mean, unbelievable when you think about it. It's the 70s. You couldn't major in computer science yet. There were graduate programs, but no undergraduate programs. So I was a double E major, but I decided to go to graduate school in CS and never looked back.
And by the way, I did a distributed tic-tac-toe program in graduate school. It was real state-of-the-art. But fast forward today and what's happening, I mean, would either of you have been surprised if someone had painted that picture for you back then?
You mean our careers?
No, well, no, not your careers, but just where we are in technology. Because I know
yeah,
I
when Gordon Moore did his prediction, he wrote an article in IEEE, some IEEE magazine, where he laid out the future, right? There's little cartoons that show people, computers in cars and selling computers at the store, and I don't think I believed it.
Yeah, he actually has a cartoon where somebody's selling a home computer right in this. But even Gordon was hesitant. He said, we can predict about 10 years, but I don't know longer than that. So I don't think anybody would have guessed. Who would have guessed that microprocessors would take over the entire industry, right, and replace mainframes and supercomputers eventually? Who would have guessed that the explosion of big data and what's happened in machine learning? I don't think any of us would have predicted it.
Machine learning is something that's been around forever, and suddenly, in the last 5 years, it's on the front page of all newspapers.
Yeah.
That would have been hard to predict even 10 years ago.
Yeah, it's definitely been pretty amazing. And speaking of Moore's Law, what is going on in Moore's Law right now?
It's over. It's over. The reason it's hard for people to believe it's over is people said 10 and 20 years ago it was over. Mm-hmm. It's over. It's double the number of transistors every year or two. John has, in our talk, John's slides show it hasn't continued. That doesn't mean there won't be more technological improvements. It doesn't mean we're frozen, but it's not doubling every year or two. It's doubling at a much slower rate.
Right. So in the last 5 years, roughly, when the slowdown really became clear, there's about a gap of 10 already built up over the last 5 years. So it's going to continue. There's another problem which doesn't get talked about as much, but is actually much more acute, and it's a thing called Dennard scaling. And Robert Dennard, who you all have used his technology, he's the person who invented the one transistor DRAM cell. Everybody uses it every day. He made a prediction that the amount of energy, actually the amount of power per square millimeter of silicon would stay constant. What that meant was that the energy per computation was dropping very quickly. And that was because of voltage scaling and other things. That's gone away, which is why you see processors today that have to slow their clock down or turn cores off to prevent overheating, because that factor's gone away.
In fact, the second generation TPU is liquid cooled, right?
Yeah.
Right, that's the third generation? Third generation, I guess, is liquid cooled, and that's because of the Dennard scaling ending.
And liquid cool is fine when you're in a big data center, but I don't think we're going to liquid cool my phone and then put a backpack on my back with a radiator. I just don't see it.
It's become a power game.
Yeah, it's become a power game.
And it's interesting. And carrying on with that processor argument, I mean, if we could just go into, you did MIPS, you did the RISC, and bringing out new chips, and we could go through what it meant to bring out RISC, and then maybe we could go through when can you bring out custom chips and why would you? That's a big question. There's plenty to, and actually, I just have to pause. We're going to let the audience ask questions. We're going to have 20 minutes for questions, so please think about your questions. We'll give you plenty of time.
Yeah, in about a half an hour, the questions will open up. So RISC got started in research at Berkeley and Stanford. We not only argued for the ideas and built simulators and compilers, we both built chips.
What does RISC stand for?
Reduced Instruction Set Computer. So the idea isn't very hard. It's software speaks to hardware in a vocabulary. That vocabulary is called the instruction set. The prevailing wisdom for the big computers was a really rich, big vocabulary with $5 words, that was going to make it easier for the software and hardware. John and I thought the opposite thing to do. We should have a simplified vocabulary with simple instructions. And the question was, how many more instructions did you have to execute, and how fast could you read them? And it ended up, maybe we needed 25% more instructions, but we could read them 5 times faster. So that was our research results. And in San Francisco, Stanford students and Berkeley students got up at the leading conference here in San Francisco in 1984, presented chips that were arguably better than what industry could build, which was kind of amazing.
How long did that take to go from the idea to that?
It was 4 years, I guess.
Yeah.
4 years.
Yeah.
How long would that take today?
I don't know, less?
Less.
Yeah.
Certainly.
Just curious.
You know, lots of things were changing at the same time. The early microprocessors, people were all programming them in assembly language, and they were switching over, so that change was occurring, which meant that you cared about what the compiler could use, not about what some clever assembly language programmer could use, right? Unix was just coming on the scene. We were going to have an operating system written in a high-level language. And then the technology was changing, right? Yeah. Many computers were still built with these bit slice technologies, and the microprocessor was a different technology with different set of trade-offs. And all those things added up to a discontinuity in how you should think about designing computers.
And so, was it well received?
we were seen as Molotov cocktail throwing radicals. The prevailing wisdom was that these richer instruction sets would be better for software. By going backwards to these simple primitive instruction sets, we're going to have more software projects, more projects would fail because we had these dangerous ideas. So we would go to places like this several times between 1980 and 1984 and participate in debates where people got angry and would shout. And John and I would be on one side, and the panelists, and then the whole audience would be on the other side. So we'd try to make our points. And after a couple of years, they finally started to come around.
But industry was very resistant. I remember one famous computer pioneer saying to me, well, the problem is you're going to threaten their existing revenue because you're bringing out a technology which is much more cost effective. So you're going to take that mini computer that they sell for $200,000 and replace it with a box that costs $25,000.
Sounds kind of disruptive.
Yeah, it's disruptive, right? And that always worries people, and that's exactly what happened. There were a lot of people who didn't believe it and didn't believe it was going to happen. And
there's people today that still don't believe RISC is a good idea.
But Intel was getting faster at such a fast rate while you were doing that.
Yeah, so lots of things happened with Intel. First of all, they discovered that the really clever way to implement a so-called CISC instruction set is to translate the instructions into RISC instructions and then build a pipeline of the RISC instructions. And in fact, that happened, and they did it effectively in the Pentium Pro. And that made a big difference in terms of their efficiency, right? Caches consumed more and more chip area, so other things mattered less. But there's one difficult problem you can't overcome that they've never overcome, which is design cost and design time. Right. So Intel's just fine if they have a 2 or 3 year design cycle and they have a team of 400 engineers. But in this world where, for example, in the mobile world, you have to have 5 different chips, not just one chip that covers the space. You need people who can really do the designs quickly, can verify them quickly, can get them right, and ship them quickly. And that's really changed the whole space.
And RISC is an advantage.
Yeah.
And that's why RISC is today just taken over.
It's the design time, and it's because of what John said about the energy. If there's less transistors, that's more energy efficient.
And when you have to sell chips for $10, or in the IoT space, you've got to sell a processor for $1.
Yeah.
You're not going to sell an x86 that's got to have a gigantic translation mechanism for $1.
Yeah, the price is really going to have to come down there. It's for sure. And so what's going on? I mean, Apple's now making its own chips. Google's making its own chips. And You know,
Yeah,
that just wasn't happening back then.
Yeah, right. I mean, Google started buying everything off the shelf, right? And over time, it started designing its own boxes and then its own networks and stuff like that. And so, you know, as John has said earlier, you know, it used to be these horizontal companies, and they're becoming vertically integrated. I think that there's the data
Is that something you were glad to see? Or
yeah.
you didn't,
Am I glad to see? Yeah.
or you didn't
Well,
care?
for me, if you're in the business of selling ideas, you want to find people who are anxious to try new ideas. A problem has been, you know, when there was just say Intel and ARM are the two purveyors of instruction sets and chips, you have to go convince them. You write your papers, you go beg them, they're gatekeepers. These more software-entered companies may well be more open to more innovations because it just has to work inside their companies.
And it's driven by where the innovation opportunity is, Diane. So you know, for a long time, we were on these general purpose processors that kept getting faster and faster. And then as efficiency of those processors became lower and lower, we had to look for another route. That route is trying to optimize designs for particular domains. So machine learning, building things like the tensor processing unit that's tailored at that. Well, who has the expertise that's required there? It's the vertically oriented companies that have the software expertise, that have the expertise to build a language and translation system that can target that hardware. So it's an interesting change. I think we're going to see people who do computer architecture work have to become much more like Renaissance people. They're going to have to be able to talk to people way up the software stack and understand what they care about in a very different way. And I think that's exciting for the field.
Yeah, it is because it was getting so specialized,
Yeah.
It's almost a reversal. And then you look at the cloud where you see so many workloads, you know, so probably the cloud vendors are seeing more workloads than the processor vendors get to see it.
Right. Yeah, yeah, I guess the excitement, well, the other excitement is the cloud vendors, it's a closed ecosystem, right?
Yeah.
If you decide, inside the company, they only have to work in one spot, right? You don't have to make it for the general purpose market and all kinds of crazy situations. It's got to work. It only has to work there. So I think that can shorten the lead time. And so far, these big companies have been pretty bold about making bets in this area. You know, Microsoft's making a big bet around FPGAs. Google's doing it around custom chips. Rumors are Amazon and others are doing exotic things. So it's a very exciting time where a lot of innovation.
Any rumors about Alibaba, Tencent?
I think they're doing chips too, right?
Yeah. I think it's an interesting time because one of the things that happened that we didn't expect was, even though we switched to high-level languages and standard operating systems, in the 80s and 90s, shrink wrap became more important because of the domination of the PC in the space. Shrink wrap software became really important.
Yeah. I guess
and that
was just the
actually
volumes,
reduced
right?
the choices.
Yeah, the volume of the PC.
The volume was so large that became the focus. I mean, even look at companies that build software, even some that started originally building software for Macs, converted to PC-only companies because it dominated the space.
The volume, yeah.
And that limited the amount of creativity and the amount of innovativeness that could go into that. And once we get that innovation quotient up, I think we can do lots of new things.
It limited the innovation because it all was for one person defining the processor they all had to work on.
Well, binary compatibility with the x86 instruction set was extraordinarily valuable. And I guess another way to think about it is right now is I think what the companies are doing vertically, they're raising the level of abstraction. So when we go from, you know, x86 binary to TensorFlow, that's a really, or Python, that's a big jump. Yeah. And if we go way up here, then there's lots of places to innovate and do things better.
Yeah, that's pretty cool. What about in the languages and the frameworks?
Well, these, independent from what's going on in the hardware, there's this move to try to make programmers more productive. And, you know, today, if you take an introductory to computer science, you learn Python, which is a very cool language with all kinds of powerful features and these Jupyter notebooks. So really, productivity is the same thing. So is the word. And so we're seeing in general, these scripting languages like Python, and then domain-specific things like TensorFlow or Halide or other things that are for narrower to improve their productivity.
Yeah. And I think that's probably the right way to go, because we're going to, if you're going to get performance out of it while maintaining software productivity. I mean, it wouldn't help a lot if we forced programmers to do a lot more work in order to get hardware performance up. We've got to find a way to get both at the same time, and that's going to require some innovation on the programming environments, probably not just the languages, but also the entire programming environment and how that works and the feedback it gives programmers.
And that'll feed on itself, because everybody, the third graders will be programming by that, everybody in the world will be
Well, imagine third graders using machine learning.
Yeah.
It could be incredible.
Yeah. Wow. I mean, will there be lots of different processors for machine learning, I've heard you guys talk about what's happening in machine learning. It'd be really great to get.
It's this, I think in our careers, it's an unusual combination of a fast-moving, exciting application area that needs, because of the end of Moore's law and Bernard scaling, needs custom architecture ideas. So here's this, you're trying, typically in computer architecture, it's like skeet shooting, right? It's going to take a few years, we want to be over there. Well, the skeet's like on, is on jet. Who knows where it's going to end up? So we have all these companies building hardware that's better than standard microprocessors for this, but who knows who's got the best idea, especially since it's moving fast. So, we're going to see, there's 45 hardware startups right now around machine learning. So we expect to see many, many ideas being tried, and we'll see who wins, Historically, if we look back in computer architecture, the marketplace figures this out. Everybody tries these bets,
and you don't think they're going to be held back by the software needed to get their processor used?
The argument is since we've raised the level of abstraction, that's what people want to program in. Otherwise, that's the classic problem.
Yeah, that's the classic problem. And I think the world's changed in another important way. If you think back to the 80s and 90s and even the early 2000s, the desktop was still the dominant computing paradigm. Desktop and the small server behind it. All of a sudden, it's cloud and things you carry in your pocket or IoT. It's not the middle of that space anymore. What does that say? That says there's a much greater variety in terms of energy, performance, cost trade-offs. I've got to be able to build processors that cost $1, and then I can have a next generation Google Cloud with a second generation TPU that's actually liquid cooled, right? Yeah, exactly. Yeah. So that's a very different range of environments, different set of concerns. So it allows a lot more flexibility.
And as I think about it right now, what's in the middle? Binary compatibility is in the middle, right? And does binary compatibility matter in the cloud? I don't think so. Does binary compatibility matter for most IoT? I don't think so. So that lets us innovate, right?
Yeah, so all these constraints are getting removed. It's pretty cool. And then along comes maybe quantum computing. Could you tell us what that is and what you think about that and when it might happen?
Tell them what it is.
So quantum computing is the technology of tomorrow. The question is whether it always will be or not. And that's an open problem. The way I like to think about it is, if most of the people working on it are physicists as opposed to engineers, then it's more than 10 years away. And right now, most of the people are physicists. Whether or not they'll be able to, the real challenge in quantum is whether or not it can scale.
Right.
It has, for certain problems, it has tremendous advantages, right? And the one problem it happens to do very well is the factoring problem, which poses a challenge to all the cybersecurity mechanisms we use, because the RSA algorithm depends on being able to factor large integers, not being able to factor large integers quickly. So that would create a real difficulty. There are other areas where it has great advantages. Quantum chemistry, for example, being able to simulate chemical reactions at an extremely fine level of detail. But to do that, to do interesting versions of that problem, which you really care about are larger organic molecules, now you've got to build a pretty big quantum computer. Remember that a quantum computer is operating at a few millikelvins above absolute zero. So physically, I have to keep something that holds that computer at a temperature which is very close to absolute zero. That's very hard to do.
Right.
Vibrations in the room, sensing the data. You walk near a quantum computer that's not adequately shielded with a cell phone, the state of the quantum computer will completely change. So whether or not you have to maintain this quantum state in order to get it to do its computing, but then eventually you have to sense that quantum state. The physics is incredible. I think we're going to learn a lot about that domain. How general purpose these machines ever become, that's an open question, I think.
But I think of it as like the computer equivalent of fusion reactors, right? It's a really good thing to work on. If they ever get it working, it'll be transforming, but it's at least 10 years out. And it's not, we're not going to have quantum cell phones, you know. So, so I'm glad people are working on it. I admire people who take these long-term things, but, in my career, it's really hard to see 5 or 7 years out. So I've enjoyed working on things with a shorter horizon.
Like 2 years, 3 years?
No, we do 5-year projects hoping to change the world in 7 years.
Yeah.
But, we're often wrong. So the longer your horizon, the harder it is to be right.
That actually, you're sort of bringing up research, and of course, both of you have spanned academics and industry, and the relationship between those two is perhaps evolving. I don't know how you feel about it, but I'd love to hear how you think about it.
I think one of the strengths of our field is we have this synergistic relationship between industry and academia. There's other fields like biology or others where there's an adversarial relationship. Is somehow, one side is you're selling out if you go to industry and you only do research. We've never had that attitude in our field. I think there's an issue
Really? Not even when all the machine learning people keep leaving being professors?
Well, I was gonna say,
it's a small problem. It's a small problem because if all the machine learning people leave to go to industry, then nobody's going to educate the next generation of machine learning people.
No, industry will.
Maybe, perhaps.
Yeah, I would say that the last 5 years, because
or AutoML will solve it. But
well, the last 5 years, there's been this surge of interest in machine learning that has commercial significance. So the salaries are going way up. So it's a little worrying. There was a time early in our careers, there was this concern about eating the seed corn. The computer, microprocessors or the internet or something was so valuable, they were going to suck up everybody from universities. And then if they did that, there'd be nobody to educate. So I think right now it's in machine learning. It's an issue, but in the big picture, there's always been bright young people who want to be academics, and they're not getting 100% of them. Well, he was president, so what do you think?
Well, I think the great thing, as you said, the great thing about our field is this give and take, this back and forth, and a mutual respect between what happens in industry and what happens in the academy. And lots of fields, that's not the case. They think, the academicians think that people in industry are all doing boring work, and the people in industry all think the academicians are doing useless work. We don't have that in computer science, and I think partly because it's a fast-moving field. There's a lot happening. You can do research which 10 years later can change the field, and that's an incredible thing.
And is that generally going on where the longer-term research for computer science is in academia and the shorter-term stuff is in industry, or is that?
That's probably true.
Yeah, probably true, although clearly there are people making some investments. DeepMind is a long-term investment.
Right.
Both Microsoft and Google have big investments in quantum. Those are long-term investments. Think of those in the same way that AT&T once thought of Bell Labs as a long-term investment, and certainly it was an investment that paid off well for the country.
And so engineering as it evolves, I recently heard a talk by this guy at Arizona that's kind of got a brand new engineering school, what's his name? Michael somebody?
Michael Crow?
Yeah.
At Arizona State?
Yeah. Is that?
I don't know about it. Do you?
Well, I think people are certainly reinventing engineering. I think there's been a lot of, computer science has had the great advantage compared to other engineering.
He did away with departments.
Yeah, he did away with departments, and he has basically an integrated school.
Yeah.
Clearly, there's a lot more interdisciplinary things, the number of disciplines pulling on computer science right now is phenomenal. Right? There are certain disciplines always pulled, right? I mean, the medical profession, various things. But the number of the social sciences, the big data machine learning revolution that's occurring in the social sciences is phenomenal. And we're going to discover things about the way we are as people and as a society, the way to improve our society from that big data revolution that are going to be really important. And I think computer science, I was astonished because when I became president in 2000, when I became president of Stanford, I thought computer science had had its run.
Like
it was going to be fine, but the biologists and the medical people were going to drive it, right?
It was the century of biology.
Functional genomics, it was the century of biology. Functional genomics, all these kinds of things. And not that functional genomics is not important, but computer science may be the most important thing for functional genomics to actually find out what it's trying to find out.
That's right.
So we've seen this incredible revolution. We've seen a growth in student demand.
Yeah.
We finally are seeing an increase in the number of women in the discipline, thank God, after many years of struggling with it. I think those are all healthy things. We're attracting the best and the brightest young minds across the whole country, across the world, are coming to work in our field. That's really exciting.
Because the field is about the whole world. And
it's changing the world. It is changing the world.
Yeah.
And both business and the disciplines.
Yeah, and you know, when John and I got into this, it was, I think our relatives didn't think we were brilliant to go into computing. It was like, okay, if you want to. But now,
my father told me, you know, hardware's okay, but don't do that software stuff.
Actually, my father told me to stay out of computers, too. Anyhow, just one more question, and then we'll turn to the audience. And I don't know.
And there's microphones somewhere there. Oh, there's one.
Yeah, there's two microphones on either side. But, and I don't, you know, maybe there's nothing to say here, but I just, you know, tech, and it's drawn so much money, and you've had so many students found companies, John's founded companies, and so on. And how, you know, and we have Bill Gates, who's gone off, and he's a full-time philanthropist now. How do you think about, I mean, and you've kind of done philanthropy all your life in that you've been teachers, but how do you think about philanthropy in the world and everybody in tech? And
well, look, a thing that I guess, I had some time between I got the job offer and when I showed up at Berkeley, so I read a book that was where they interviewed, it was called Working by Studs Terkel, who he interviewed a lot of people about their careers.
Called Working what?
It was called Working, where he interviewed, say, 40 people in different disciplines.
Mendel told me about that.
And what I got out of that book is that the people who either they built things that lasted forever, like the Empire State Building or the Golden Gate Bridge, or they worked with people, like priests or teachers, really felt a lot of satisfaction that they affected people's lives. So that was, I kind of went in expecting that. And then I think in America, you kind of grew up thinking if you're rich, you're happy. But, you know, if you're trying to be happy, you could just try to be happy directly, and rich may not be part of it. So I think that's kind of driven what I did. And people have started studying what makes people happy, and one of those things is helping other people. That makes you influencing people, you know, helping them is a thing that makes you happy. So, yeah, I think if you'd like to be happy, you should help people.
Yeah.
Yeah.
You know, I think it's been fascinating to watch. I remember a discussion I had with Bill Gates probably now 25 years ago, asking about what his philanthropic thoughts were. And he said to me, I'm too busy running Microsoft right now. I don't have time to think about it yet. But if you've met Bill, you know he is an extremely focused, driven individual, and you'd know that from the way he ran Microsoft as well, and what he managed to do there. When he became a philanthropist, he became a real philanthropist. I mean, he can sit down with our faculty in the medical school and talk about biology and infectious diseases at levels that few can other than professionals. And he and Melinda are really committed to making a difference in the world, to measuring it. I saw that happen. Gordon Moore now and what they've been able to do at the Moore Foundation and putting money into their two big things are science
I have to
and
say, Bill
conservation.
Gates seems like one of the most joyous people now.
He is happy.
Yeah.
Is that right?
Oh.
He is
Boy.
happy doing his
Bill
work.
Gates happy.
He's happy doing it. They really love it. And it's a team. It's a team effort for he and Melinda. I mean, seeing Gordon Moore do it and being able to, I was up in Alaska visiting work they're doing on conservation in Alaska, and seeing what they've been able to do to restore wild salmon habitat that was in danger of vanishing forever. I mean, it's phenomenal. Sitting with Mark Zuckerberg and Priscilla and talking about their philanthropic ambitions and their desire to really reduce the damage of human disease. I think in each case, each one of these people, it's given them something really exciting in their lives. Early on when I was president, I was looking for some inspiration about how to inspire people to become more philanthropic.
Yeah.
And I read a book by Ron Chernow, the person that wrote the Hamilton book, the famous Hamilton book, about John Rockefeller, the creator of Standard Oil. He had a heart attack and he almost died when he was 50. He retired. He became a lifelong philanthropist. He started the University of Chicago. He started the Rockefeller Foundation. And he lived to be well into his late 90s.
Whoa.
And had a joyous life.
Yeah.
So I think giving back brings joy to people. Doing it well, which we're all smart people, we're creative, we like to do it well, I think is something that can really help make the world a better place.